Okay, hello and welcome to this video. In this video, this is just a random video, but I'll be designing industry standard device, basically your instrument to measure temperature, and we'll be using a Modbus protocol to read the temperature, and we'll be using very cheap materials, STM32, to read the temperature, save it into the registers, and basically expose it for the PLC or controllers to read. So this is just an idea to replicate the common devices that are majorly used in industries, and I will try to cover as much as I can in this first part of the video. So we will be focusing on the hardware design initially, just a basic and relevant subsystems of the device. And then maybe if the video is not too long, if the video is too long, I'll do a part 2 of this same design and just write the firmware for it. So without further ado, you can see I have opened my EZDA design tool here, and I've not like designed this before. I'm just like just implementing an idea I have in my head, and if you notice any mistakes, just bear with me, and maybe hopefully we'll correct it in a first revision, or notice it within the video itself. So I'll basically create a new project here. I mean, you can feel free to like skip ahead and just go to the right parts, because I will set the baseline initially for the first few minutes, then we start designing. So the device I want to design is basically a temperature sensor that uses an NTC, or the negative temperature coefficient device sensor to read temperature, right? So I'll just call it NTC industry sensor RS485, right? RS485 NTC, yeah, NTC, yep. So click on save. It should save this project and provide us with a schematic basically to edit. Anyway, meanwhile, this is what I have in my head. So right here we have the STM32. We can use STM32, or we can use STM8. Let's use STM32 for now. We'll optimize on cost later anyway. Then right here I will have the primary instrument is an NTC temperature sensor right there. Okay, then I will have power supply. So most industry standard instrument use 24 volts for supply. So 24 volts is just easier to it's very common to find. So power supply right there. So this feeds that, this feeds that guy. Then this is red here, right? And then the other thing, I want this device to have a simple screen, so we'll have an OLED 0.96 inch screen, right? Screen will be feeding into this. Okay, so that's that. Then in industry, like these devices, rather for the most that I've worked with, they have a way of user settings. They expose user settings, the ability for the user to set things to do with device address, for example, register addresses, communication settings like bound rate, if you're using 8 bits, parity settings, etc. So what I'll do, I'll use a keypad, right? Just let's say we use 4 buttons, right? I don't know whether there's a button here. 4 buttons. Let me use this. So just to like make it more visually sensible, so I'll use this as menu, right? Menu. The next thing we want after menu is an up button. Then we want a down button, down, right? And then maybe okay, menu up, down. Then let's say we want right. Let's say right button. Let's just put an arrow. Those are 4 buttons, right? So those four buttons are connected to the STM32 right there. So that is that, and that is that, and that. Okay. So for now, just it's not like a most clean design, but just make it simple. All right. So what I like to do is like to label the arrows and the communication types I'm going to be using. For example, for NTC, I'll be using, this is basically a DC supply, right? So that's ADC right there, analog digital conversion. OLED, to make it simple, I'll use an I2C protocol. Next thing is let me just reduce the font here a little bit, reduce also the grid size so that I can move these items more precisely. Okay, this is 7 pixels, this is also 7. Okay, good. So power supply, obviously it's power supply, there's no problem about that. Menu, these ones are going to use GPIOs. They're just 4 buttons, so I can use 4 pins. If you add more buttons, you just use a multiplexer or an IO expander, right? So GPIO right there, and then here we'll use another GPIO, and this is GPIO as well. Oops, this is also GPIO. Okay, so maybe another user interface item is an LED. You never miss an LED. You always have LEDs, right? So this is audio, this is not LED. So I just have a circle, call it user LED right there. Okay, so you're going to design that. So this is going to be a GPIO as well. Right, so that is our instrument. Very simple, and you'll actually find this, like the instruments I've worked with, I've been investigating them one by one, and you'll find very basic design architectures inside them, but they expose only what you need, and the design philosophy is so simple that you actually wonder whether that instrument is really verified to be used, but it is actually simple. It's actually best to design a simple system and then improve it later if need be, right? So NTC industry device, another instrument, right? Okay, good. Right, so that's that. So let's design this. Okay, so one thing I need to say is that for Also, these industry standard devices, they don't allow you to do things to do with resetting of the MCU or booting of the MCU. They just come preloaded with the firmware, right? So your work is just to read the registers. You can't reset the MCU, right? That's the developer side. Developers has done their job. You as a user should just read the temperatures. Anyway, so the next thing that I'll do now is like start scoping for chips, right? So I'll go directly to LSCSC and then to STM32 site, right? STM32 for example, go to their site and try to look for STM32 devices. Let me zoom in a little bit. STM32 F103, right? Let's go STM32 F1. Let's go with F1 series for the F1 family. We want just minimal subset of tasks, right? Just minimal ability of task. Cortex M, mainstream. We don't want high performance. We don't want wireless. We don't need ultra low power. We just want let's try mainstream, right? F103C8, 32-bit, 372 megahertz. This is an overkill for just a single temperature sensor. You'd see that you'd ideally use something like an STM8, right? Motor control USB can. I mean, let's just use this. It's a mainstream device, which means that the STM is going to be producing it for a long time, right? So I'll just copy that and just to accelerate this development, open LCSC and search for this in that to F103C8, accept, and you can see they in stock. I'll just take this part number, bring it up here. So one other thing I like to do is I like to segment my schematics so that they are easier to read and review. So if this is a schematic, you can see it should have multiple pages. The first page, I always set the first page to a block diagram, right? Block diagram, just for documentation purposes, right? The next thing that I do is I'll say MCU, right? And then the next thing is basically the sections we have described in the block diagram here. These sections, it's just what I'm translating. So MCU, create a new page, right click, new page. Then we rename this to, rename this to, I mean, you can fast forward if like this is raw video and cut, so you can just fast forward to design part. Or just take time to rename this to power, and then new page. I'll rename this to which is the other part, rename to user interface. User interface has the LED screen and the buttons, right? So anyway, MCU, shift F, it's a shortcut to start part search, LCSC. Remember we copied our part number from LC, just paste it there, Control V. We get our device right there. Okay, we get our device right there, zoom out, and there it is. Okay, so one is enough. It's in the 1213. The next thing I'd like to do is just ground all the ground pins. So up here on the VCC channel, you click on that and you ground all VSS, right? So this is grounded right there. This is grounded, this is grounded. What else is grounded? This guy is grounded. There's no other VSS. Okay, good. The next thing I like to do is add a power supply, which is net. I like to use nets, global nets. So I'll just say this is 3v3. So VDDA, this guy, I'll rename it to 3v3 plus. Okay, so don't bother about the cleanness of the schematic. We'll clean it later. But VDA VBAT also is 3v3. Again, you can always refer to the data sheet, but I think I've designed most of these boards, so most of these things are just off the top of my head. And if you notice a mistake, again, as I said, just bear with me. Maybe I'll notice it too in a few minutes. Okay, so I just pull this out a little, put that out, and then just to make it appear better, like that. Okay, so yeah, that's good. The next thing I do now is basically handle the power. So there is how many pins to do with the power. We have to filter using capacitors, right? So what I do is I'll take 100 NF capacitor. So I'll just come here and say look for C005 100 NF capacitor. You can search with the voltage also, like 16 volts. It's too high, but it's derated. The higher the voltage, the less the higher the voltage. If you're using 3.3 and you choose like 25 or 50 volts, the lower the performance. This is more of ESR and DSL shenanigans in there. So I'll copy this, the first one. You can compare prices if you want, but this is not a detailed design video, so I just copy that 100 NF and just place it somewhere on the top. No, let me place it here. So for every power pin, you place a capacitor, right? These are 1, 2, 3, 4, 5, right? 5 of them. So we need 5. Let's copy paste those two. And copy paste that. Then connect 3v3 to this design part. I mean this top of that capacitor to the end of this, and just link these terminals. Next is ground the other part. So ground it. Again, this is a basic device, so there is more that goes into decoupling and coupling capacitors. So this is 100 NF. The next thing that I typically you look for a 1 NF capacitor, and not 1 NF, 1 microfarad, 1 UF capacitor. Let's see, 25733. This is okay. That's good. So paste the number right there, place, and then just place it right there. I'll just use one of those. Just one of those. Okay. So the next thing that I do, so we have the power handled. The next thing that we do is how do we add clock to this device? So there are two clocks. There's a low speed oscillator clock and high speed oscillator. So I like to use 16. This device, if I open the data sheet should be somewhere. Should use 16, but let me just confirm that it's using a 16 megahertz or a 8 megahertz clock. you can data sheet. So we go to clock, not here, electrical characteristics, let's see, let's look for clock. Okay, 4 to 16 megahertz crystal oscillator, right? So you can use 8, you can use 16. So 16 megahertz crystal, right? So I'll just the one that has a place ability and is in stock. So I can use this one, 0.3, 0.3, 0.1. Place this 0.4. This is expensive. 0.3. Let me use this. A difference of $0.1 is a lot of money anyway. If you do it at scale, right? So just add the clock right there. Oops. Okay, so these two pins are the ones we want, right? So you'll take that, pull it right there, take that, connect it right about there. Or to make it more interesting, let's just put this there and take a net. Actually, take a net and put those two. They have no polarity, so we can take these as, these was 16 megahertz, right? So yep, so just close this. HSE, high speed external 16 megahertz in. Then I'll just copy that and paste it here, but this one will be out, right? So I'll just take those two pins, this and that, and copy and paste them. I'll do this, connect that one there, connect this other one right there. Okay, so just pull these two a little bit to the side, right about there, and then I want to now like clean this part of the oscillator, right? So the first thing that I'll do is connect these two pins to ground. So these two should go to ground, but I'll just do that. And that, right? The other thing is the capacitors, that these devices, these crystals need capacitors to run, right? So I'll go to the supplier part and just search. Actually, I just search it here. Data sheet. Come to this part. This 20 picofarads. There's a formula to calculate that, but let's look for. So it's given as 20 picofarads. This is the data sheet they have. The frequency maximum 5. Shunt capacitance maximum is 5. So I'll use 5 picofarads to C005. There's a formula to calculate that. I don't want to look for it at the moment, but we'll update that in the description later. So place this shunt right there and a shunt right there, and then ground it. ideally your ground should be facing downwards, but anyway, we can change it later. So right now I'm optimizing for speed, and yep, that's that. The other thing that we need is let me refer to a specific design document that I have. Just a second. I refer to my previous design that I have done. Let's see. .pdf, PSF. Okay, let's see about that. Okay. What now? This is my another project I'm doing, but I'll just confirm the schematic for 16 megahertz clock. So it's just that, yeah. Ground is this is the formula I was talking about. 2 times load capacitance, and you get what you need, right? So 5 PF will do just fine for now. Okay, right, that's that. So I'll just minimize this and we go back to our design. Okay, clock is fine. We don't need the 32-bit, I mean 32 crystal, so I'll just like leave that unconnected. We can reuse the pins if we want, but actually let me just get it done with the PC13. We'll use it for the onboard LED, right? So let's add an LED here. So it's an industry instrument, and we want that LED to be exposed to the user, right? So because there's a casing around the device, we can have, there are two things. You can have a through hole LED that has long legs that protrude close to the rather close to the casing, so that you just see the LED itself, or you can have a surface mount LED and then add these translucent LED guides, right? But adding LED guides will make the manufacturing of the device more expensive than using through hole. So I'll just go with through hole discrete LED. In terms of, I'm just explaining my decision because cost is also a major part of device manufacturing, right? So okay, what is this? I think it's LED. Let's see whether we have. Sometimes LED searching is just, I don't like it because it doesn't bring you the right results. Anyway, I'll go to the catalog and search for these optoelectronics, LEDs, addressable no, indication white light, discrete, right? So we should have filters. Where are the filters? DIP 23 millimeters, DIP 3 millimeters. This is not an issue. Viewing angles are not a problem. Then we apply the filter. Yeah, so this is the LED that we want. So let's just use a green. Is there a color here? Color. Let's just use red. There's no problem. Apply. That is okay. It's in stock, 0.05. Good. So we just copy this part number. Just copy it, bring it back here, place the device. So what I'll do I'll place this on the user interface schematic, right? I'll place that there and rename it to user LED, right? The one major thing that accompanies LED is a resistor for current control, so the current protection. 500 R. Red to, if you want to know the value that you need to do here, you can always calculate. The supply is 3.3 minus 2 volts, average for a red LED. That's 1.3 divided by 20 milliamps if you want, right? So you can just say 1.3 divided by 20 times 10 raised to minus 3. That will get you 65, but 65 is too low, so I'll just use 500, which is okay as well. There's no, just a ballpark figure. Resistor. Right, I'll just pick this first one. Resistors are pretty cheap, so if it's a critical device, you can always calculate the rate, the power rating, the wattage of the LED, like the wattage of the resistor, etc. There's so much design you can do anyway. So I'll call this user LED. We call user LED 1 because you can have 2 in case you want to indicate a failure of the instrument. That will be okay. So I'll just copy this and bring it over to the MCU schematic and put it right there. Just align it with the rest. Save. That's okay. So our device is coming up to shape. So we have this done. We have this done. The next thing we are going to do is add an NTC temperature sensor. So what I'll do in this case, I'll not attach a direct NTC. I'll attach pins 12. During manufacturing, you can solder the NTC temperature. Let's say this device is to use for measuring ambient temperature, right? There's no specific use case that I have in mind, but let's just attach a DIP NTC right here. NTC, say 10K, with a resistance of 10K, right? So NTC, this is the exact one that I'm talking about, $0.09. Just open it, product page, to see a little bit of the 5 ohm through hole, 5 millimeters, which is okay. Let's take that and just Shift F, paste and place it. So we'll place it somewhere around here. So NTC is for a schematic for NTC looks like this, because you'll be reading it with an analog to digital converter. We'll have a resistor here, NTC, and then a change in temperature. If the temperature increases, this is a negative temperature coefficient. Temperature increases, the resistance for that device decreases. So we have that, and then this is the NTC. This is 3.3 volts. This is ground. So varying current will flow through this point, and then we can sample it. Right there. So right here we can use a 10K device, or rather 10K resistor. So the first thing I put on top there is a power supply, not a capacitor. Power supply. Then I look for a 10K resistor, basically. C0805 10K resistor. Oops. resistor, I might type resistor. Good. So million in stock. You can copy that. Just close this without saving. Don't save. Come back to schematic. Shift F, paste, place that, and right there. Okay, so ground it, and then at the junction here, this is where we measure it with the ADC. So if you want to use an external ADC, it's up to you. If you want to use for me, I'll use an internal ADC because the STM32 has internal ADC. So just connect that to the ADC. Then I'll call this is NTC. Right now, where does it go? So that's the question. So the thing is, you have to look for the pins that are using that have ADC enabled. So you come to the data sheet, you look, this is pinout and description. Does this have the functionality? Yep, it has it. So we look for pins that have exposed ADC. So what I do is just search the device. It has 2 ADCs, and then I come to analog digital converter. They are 12-bit, as you can see. The ADC can be served by a DMA, so we will be using a DMA in our firmware and etc. So what I want right now are just the pins, right? Just the pins. Okay, so let's see which is the closest. Okay, good. So ADC 12 in 10. Okay, so let's go to the next. Where ADC, where is in 1? Okay, so I'll just pick this PB1. PB1 is timer channel 4, timer 3 channel 4. This is ADC 12. I think it's ADC 1 too, or is it not ADC 12? Right, so ADC 12 in 9. So I'll just rename these two. NTC ADC 12 in 9. Let's go to PB1. So PB1 is somewhere right here. PB1 is right here. Save. Okay, so we have our temperature. We have our crystal. We have our power. Okay, so the other thing is the screen. OLED. So what I'll do, I'll just add a connector for OLED. It uses 4 pins basically: VCC, ground, SCL, and SDA. So I just look for a pin header, 4 pin. Male, doesn't matter really. Whether male or female, because we won't be adding the pins themselves. We'll just leave it as a solder joint, right? We can leave it as a solder joint, or what I'm thinking is that we can have a stacked layer. You can just insert it. So it means I actually have to use these female connectors, right? So copy, paste that, place, and I'll just copy this, put it here on the user interface. And so the first thing that I do is I'll check what's the connection of a general purpose 0. Okay, I already have I think I have a screen lying around here. So this is what I'm talking about, OLED. I just want to know the order of the pins. So the ground VCC, and then SCL and SDA, right? So this is ground, VCC. So VCC will be 3.3 volts positive. So I'll take this to be plus 3V3. And then the other one was SCL and then SDA. Right, so paste. This is SCL, this is SDA, and you can pull this out a little bit if you want. Yep, that's that. So screen is done. Next, power supply. So as I said, most devices use 24 volts power supply, and we'll use the same. So we'll have some terminal blocks here that can be connected to 24 volts power supply. So let me close this, close that. Look for terminal blocks. I'll use the large ones. The large ones are normally spaced at around 5.08 millimeters apart. They are screw terminal blocks. So yeah, so these are the ones I'm talking about. Copy that part number, paste, place it. Okay, so let's see. So the biggest challenge in this device is balancing cost and complexity, right? So it means that when you're designing like a 24 volts supply system, there are a lot of protections you should use for such a device, right? But if you use a lot of protections, it means the device manufacturing becomes expensive. So you find that there's always confusion about finding a balance, right, when you're designing such devices. So I'll go with the most basic but typical design structure or scheme for 24 volts. But before that, I'll rename this to 24 volts supply, right? 24 volt supply. So again, when you're doing 24 volts, you need to protect your device from reverse protection. So the first thing you do is use a short key. The part number is always, I think it's SS54, if I'm not wrong. And then we now filter it down to 24 volt circuit protection, transient voltage suppliers, TVS. Let's look for single diodes. Single diodes, enter that. Okay, so voltage forward, no, not these ones. I'm looking for transient VS diodes. Let's look at this and see what it protects from. 3 amperes, 20 to 100 short rectifier. Looking at the curves, maximum repetitive peak reverse voltage, SS36 will give us 36 amps, SS34 will give us 40, SS33A will give us 30. Let's take this. SS33, maximum RMS is 21. Okay, SS34A will do 40 at 28 RMS. DC blocking is 40. Okay, maximum 3 amps, fine. Okay, so I'll go with this SS35A. Come back here, shift, search for that node data. Let's see. SS35A. Does it exist even? Yeah, it does exist. So this is the part number. This is 34A. There's almost no difference. So paste it right here in place. So it's a short key, so that's that. We'll confirm this circuit. So 24 volts short key. Next thing, after reverse voltage protection, you can use a P-channel MOSFET for reverse protection, but P-channel is expensive. MOSFETs are expensive in general, so we'll use this short key. It drops way below 0.3 volts thereabout, but since our device is going to be using 3.3 volts and we are supplying is 24 volts, it means we'll have to drop around 20. This 24 minus 3.3 is 20 point what, 21.7, 20.7, right, volts. So 20.7 volts is going to be wasted, not really wasted but discarded. So the next thing, that the best culprit we can use there is now our switched mode power supply. We cannot use our linear diode, low dropout regulator because of the heat losses. So we'll look for an SMPS, and no other better SMPS to use than the typical LM2596. 2596, we can drop our voltage up to 5 volts from 24 volts, and then we handle the rest from there. So LM2596, this is 5 volts. This is exactly the one I want. So for 5 volts, right, 3 amp, and then it's a fixed 5 volts. So I'll open the datasheet and as well as copy this part number, paste that right there, and I'll just place it right there. So ground will always be ground, right? On, off, I want this device to be always on the moment you turn it on. So just, it is active. Wait, this is active. For it to be on, it's active low, so it doesn't need to be, it's not connected to VIN, it's actually connected to ground for it to be on. Because you can see this hash here is like active low, right? Okay, so turn it off, you connect it to the VIN, right? Alright, so next thing we do is we design a circuit around this this device. But what will happen is that these 24 volts will come directly to VIN, and then we design the voltage around it. So I opened the datasheet, and there's a design table these datasheets always have that you can use to design your schema, your circuit. Good. So this is the one I'm referring to. Let me just close this sidebar. Right. So this is fixed voltage, quick design reference, quick design component selection table. Right. So output voltage 3.3. No, these are fixed 5 volts. So I'll just take the 5 volts. Current load 3, which is okay. Current load can be 20. Let me go with 2 amps. Then I'll just pick this. I'll pick these values right here. Right. Okay. So 2 amps max input, oh sorry, this max input voltage will be 40, not 20, because I'm supplying 24 volts. So inductance 68 microhenries, and for that we have a schematic here. C in, right? C in is 68. Was it 68? 68 microfarads. The other thing that you can do is refer to this specific schematic right here to get an output of 5 volts. So you can see C in is right there, 220 volts, 5 amps, 68. L38 is 68. That is L1. Where is L1? L1 is the output inductor, 68 microhenries. So let's start with that. 68. Okay, sorry. Close this. This is 68 microhenries, 3 amps. See what that gives us. That's okay. So I'll just take this, copy this part number. There are more parameters that you can check, but maybe during our first review we can always review that. So I'll place that. It's an output cap, it's an output inductor, so wire it that way. Where is this? Where is the data sheet? Okay, so not that one, this one. Good. So this is done, this part right there. The next thing that we do is look for D1. D1 is a shortkey, is a 5 amps 40 volts shortkey. So they have given us the part number 195825. I think that's a through hole, 185895. It's a through hole, we'll have to, yeah, it's a through hole, but I don't want to use a through hole for this design, so I'll have to look for a better, this is 5, not better, but it's an SMT, 5 amp 40 volts short rectifier, right? 5 amps 40 volt Schottky rectifier. Keep Schottky die. Did this in such one? Schottky diode. I need a Schottky diode, not yeah, this type, but diode array, you can use them, but some of these are pretty expensive. Let me remove the 5 amps. Good, so this is the one I'm talking about. 0.16 is fine. Clamp diode. Let me check that. What's the current rating? This is a TVS diode, not a Schottky. What about this? 50 amps surface mount Schottky battery rectifier, 2 amps. 2 amps is fine. Can also work as a TVS, which is okay. Reverse polarity, maximum reverse 40, maximum average forward current 2 amps. I'll not even be using close to 2 amps anyway. I can go with this. This is totally fine. So copy. Can copy the manufacturer part number or the LCSE part number. Both work fine. Paste and place it. It's placed. So let's again refer to. Where is that schema data sheet? Yeah, so it's between output and ground before the inductor, somewhere right there. So I'll place it right there. Okay, so the other thing is this C out. C out is 220 35 volts electrolytic capacitor, 220 microamps. I mean microfarads. Sorry, 220 microfarads, 35 volts. 35 volts SMD. There's an easier way to design this by using a test bench, TI test bench, power design test bench, right? But anyway, I think I got stuck with this method that has worked so far for the designs I've done. I just think I'll keep using it unless I'm really pressed for time. Then I can just try other routes. But again, let's just check that. Let's check the after the inductor, right? So ZDA after the inductor. So this is the output side, by the way. Even though it's oriented, like ideally you want to have the inputs on your left and your outputs on your right. Okay, so after that we have the regulated output, which should be 5 volts, right? So so this should be, or rather will be 5 volts. Okay, so we have designed the output side. Let's go to the input side. Input side, you just need one capacitor right there. C, you see what? C in, that one. C in is 470 microfarads, 50 volts. Again, this design, this LM2596 comes like there's a lot of values. L1 inductors, capacitors value values you can play with. So you'll find someone else using different values of capacitor and inductor, but they produce the same output. Yeah, so for easy design, just go with what datasheet says you should use, right? So what am I looking for? I'm looking for 470 microfarads SMD capacitor. SMD capacitor. I'll take this and paste it right here. Place. Let's see. All right, so it's on the input side, so I'll just put it somewhere there, and then put that there. Where is the document? Right there. Okay, so V in, then to ground, on, active low, feedback, right? So let's look at this part. So V out is equal to V ref which is 1.231 plus R2 over R1, right? So R2 is given by R1 V out over V ref minus 1. But this what SMPS is like fixed, so ideally we should be using this schematic, but you realize they are the same, right? These values are just the same as these values right there. There's no difference. For 70 to 20, 5 amps, 40, 68. 68, 5 amps, 40 to 24, 70. The same, fixed. So feedback is directly tied to the end of the inductor. So feedback to the end of the inductor right here. Let me just confirm that from this point to this point. Cool. So let me see how I can connect that. I'll just do that, and do that. I mean, there's a neater way to do it, I think, but that should work. So we have our 5 volts. Good. Okay, the next thing we do is we take these 5 volts and drop it to 3.3. So if you come to LCSC and check just 3.3 volt, here we can use an LDO because you're just dropping 2 volts. Ideally you can use an SMPS, there's no problem, but cost again, 3v3 LDO, say voltage regulator. See what pops up. A typical AMS at 3.3. You can use it, but it has a larger footprint, not fingerprint. There are a lot of other, for example, this SP1117, same footprint is the same. You know what, doesn't really matter. Let's just go with this. I was just looking for another one, but there are several others you can use, smaller ones if you're like lost for space, if you're pressed for space. My English is just something else. Okay, so we take these 5 and we feed it here, and then output. Now this is the output. This is where we get our 3v3. This is where we get our 3v3. Okay, so capacitors are adjustable ground, so we can connect this to ground, this one to ground. Just do that, and then we add 1 microfarad capacitors, C005, 1 microfarad, to just filter, to decouple the LDO, right? So copy, paste, copy that, Shift F, paste, place. I'll just place that one right there, and this one right there. Then do that, ground these 3, ground that, and that too. Alright, cool. So we have our power supply done, fixed, and again there are a lot of protections you're supposed to do here. Basically, let me just add a TVS. Let me just add a 24 volts TVS diode. So if you look at 24 volts industrial industrial device temperature sensor schematic, let's just scope for a few of them. Opening new tab. Okay, so you see, for example, this one is using AC voltage, right? AC rectifier, I mean a full bridge rectifier, filtering, then you have this variable voltages, you have an LDO, these are temperature sensor. Okay, so it's fine. Power supply 24 volts, then you have these terminals, etc. They're not providing a schematic. Anyway, what I'm trying to show is that 24 volts is just typical. So in case you're asking why I'm using a very high voltage to supply a 3.3 volts device, that's the thing, just the standard. I was adding a TVS here, so 24 volts TVS. How much is that? This is 0.2, so 20 cents. Okay, copy this. Place. I'll just place it right there. Then ground it. I'll explain the parameters for this later. But for now, let's just work with it. Okay, that's that, and that's the power supply schematic. Okay, so the other thing is this is incomplete. It's just it's really bothering me to have an unprotected 24 volts, fully unprotected, right? It's an industry device, so let's see, maybe version 2 will have like better design. All right, so back to MCU schematic, further to our template. We have this, we have that, we have, okay, we have this, we have that, we have that. We don't have the buttons, and we have not interfaced the OLED to the OLED to the what? To the STM32. So if you come to the user interface and copy these two, paste them on the MCU page, we should know which pins are connected. You need to know which pins are SDA and SCL, right? Ideally, you should start this designing from the STM32 project, then map your pins and translate them to schematic, but either way it works. You can start from the schematic and go to the STM, or STM coming back to the schematic. STM32 cube ID, that's what I mean. Right, so here I look for I2C1 or I2C2. Okay, I2C1, I2C1. It's right here. I2C1 SCL is PB6. So SCL is PB6. PB6 is on this side. So right there. Then SCDA is PB7. PB7 is right there. Save. Okay. So we've interfaced this OLED and that. Last thing we need to do is, okay, not the last thing anyway, but just the major things are the buttons. This will allow us to like set our device, like in terms of what's our what's our device address, what's our communication baud rate, etc, as I said at the start of the video. So you can look for buttons on LCSC. Look for tactile. Have you got tactile buttons? Tactile buttons. Yeah, this type, right? These type are common in. It just depends on how you design your casing. We will design the casing too and see how it maps out. So I'll choose these ones. These others have like a tendency of like the membrane. This membrane just tears off after you press it for too long, rather for a lot of times, not for too long. So I'll just place this, place it. Okay. So this is supposed to be on the user interface side, just somewhere around there. So a schematic like this, I mean a button like this, when you press it should go to ground. In my designs I always take it to ground, just to mention that for a low power device you don't want to have pins that are constantly pulled high, right? Because I mean you don't want to have pins that are constantly pulled low, because they'll have what is called the leakage current. I don't know why I mentioned that, just some thought in my head. Yeah, so we'll place 100 NF just to debounce it a little. You don't need it, but it helps to debounce this switch. Just a simple RC. Okay, this is supposed to be on this other side, sorry. So this, let's call this up. Then we need a 10K, C005 10K. Yep, 10K is okay. Copy that part number, Shift F, place it. Maybe I'll place it right there, pull it up a little bit, ground this other side. Then we need a voltage level that is equal to our MCU expected voltage level. So this is basically 3.3 volts. So just copy that, come back to user interface, paste that. Then I'll just take this and call it BTN up. Okay, so this schematic is replicated for 4 buttons. Paste that, paste and paste. So we said we have menu up down, so BTN menu up, this is menu up, down, so means this will be BTN down, and up, down, and left, right, BTN right. Okay, so that's that. The other thing is to just have these buttons interfaced. So we have a lot of GPIOs to use, so I just come to this other side and paste. Let's use port A and paste this. Sorry, delete that and paste this right there. paste. This is 4. Okay, so our device is coming up to shape. Just a few more things, and then the schematic will be okay. Button menu, button up, button down. So up and down, maybe you want to increment a counter, maybe 1, 2, 3, 4. For example, in most RS485 devices, you want to set the device address. So you can have device 0, 1, 2, 3, 4, 5. So if you want to increment, or your screen is waiting for you to increment that specific part, you can use these buttons to increment it. So up, down, and then if I say right can be used, for example, what I'm thinking can be used to like go to the next level of a menu. For example, if you press menu, you have these settings, you press right and you go to the next level instead of having okay. Then this is more of a software design I'm discussing. If you are in like a level 1, you go to level 2, if you press menu, you should actually save. You should be able to save that setting, and then the device will have like a countdown timer that checks how long has the device not been pressed. Then it just resets the whole menu, or the whole screen interface, to the default setting, right? So that's my just thinking about around it. Now I think we are done with this device. Then now the last thing is, now if someone might ask you, how will you program this device, right? How will you be able to load the program onto it? So first of all, if this device is going to be sold, it means that you don't want to, the user can be able to program it themselves, but you don't want to be able to you don't want the user to be able to program it themselves, right? So there are things to do with anti-tamper that you can use, but for this version I'll just provide 4 pins for me to program the device, right? So what I'll just expose serial wire debug pins, so clock and input output, using 4 pin header. Yep, this one. You can use these, or you can use a JST. Let's see, I can use this one, but let me use a JST. It's more stable and it doesn't get loose after decades of use. Yeah, so this is a weird symbol. Okay, I'll just ground this part, then set this part to 3v3. Good, so this other one will just be a simple, a simple SW, then SWD clock. So which pins are these? We need to go back to the schematic, the data sheet, and check. What are they called? SW clock, if I'm not wrong. Yep, P14 is SW clock. P14, I think I've not used it yet. P4 is PB14. P14, where is it? It's right here. P14, and then P15. What about SWDIO? P13 is input output. So I can copy this, bring it to A13. right there. Okay, so we have exposed our programming pins. The other thing that we should do, at least for a development device, okay, what happens is when you're manufacturing such a device, the program is preloaded into the MCU. Then the MCU is, the programmed MCU is loaded onto the PCB, right? So that's why you see most instruments don't have, most devices don't have exposed programming interface like we are doing with this one, right? But since this is a development device, we can always expose our programming interface. If you are doing actual device that will go into mass production, don't expose your programming pins, because the user can easily read the program and can reprogram the device to do what is not wanted. Basically, you're just handing them off free, and these devices are always very cheap, especially a temperature sensor is super cheap, right? Okay, so I think that's the last thing we want to do is add the reboot and reset, just to help us program the device. Boot and reset, where's this is and reset, so just copy that and put it right there. Just call it this NRST, and then boot is right here. Boot is here, right? So we copy this, bring it somewhere here. So booting is just a push button that we press, and we have a push button. So I'll just copy this schematic from this side, bring it over here. So basically, when you press this button, it goes to ground, and it's always pulled high. So that is boot. Connected like that. Then this is reset. So depending on how you press or the sequence of pressing these pins, you can actually control where your program boots from. Let me just show you that. Boot sequence, it's power up sequence of boot sequence. Boot modes, yep. You can boot from user flash, you can boot from you can boot from user flash, user flash, system memory, embedded SRAM, right? You can write, for example, if you press boot plus reset, you put your MCU in program download mode. So whatever comes through SWD is saved into the flash memory. After that, you press reset, your program loads from the flash memory and it runs. That's the basic flow. So NRC and reset. This is a boot. Save. And yeah, we are done with the device, the schematic. That's 1 hour and 23 minutes of design. Basically, it's pretty slow, but it's not bad at all. Okay, so let me just rearrange this a little bit to make it neater. Just move this a little bit up there. I'll add a border. I'll add this right there. Just oops. I'll move this up here. Move this to the side. Let me just have this close to the, let me have it close to the MCU itself. We have clock right there, and then we have these the major culprit, which is the temperature sensor basically, So I have it somewhere here, then have this here and there, right? So next thing I do is just name the sections. So I'll just put a text and say this is the MCU, for example. Let's say 4 millimeters, and not the default. Let me use one Verdana. Place it, the MCU right there. It's bold, but it's too small. 6. Okay. MCU. Debug header. There's something I didn't put. A UART reader. We need a way of like reading the output of 16 megahertz HC, output of our sensor, of our STM, so basically through UART, right? So this is boot. This is NRST, NRST. This is what? This is NTC temperature, right? So I like to name my schematics as well, so just push this just like that, and then copy this, paste, rotate, and this is MCU. 5. This is going to be double that, or even 2 times that. MCU. Okay, so I'll copy these two, copy them, come to power, just paste and place it right there. So this is the power supply. Power supply is fine. The next thing is come to the user interface, paste it, and just place it somewhere there. Is there user interface? So user interface, I have that debug header, I have user LED, we have a I2C interface. This is OLED screen. So OLED screen, I need to call these as OLED, just to be able to see it very well on the seal screen during PCB. So this is user buttons. Good. So that's that. Let's just move these a little bit and correct this part. Just bring it in like that. Okay. Schematic is complete. The remaining is just the block diagram. So block diagram, we already have it. Sorry. Copy this. Block diagram, paste. I have like 2 minutes. Block diagram. So block diagram, it's right here. Let me change that. Okay, so I'll just NTC temperature sensor, NTC industry. We rename these to temperature sensor, right? Okay, take this and export it as a PNG, selection only, export to pictures. I think, do I have pictures? Let me just remove NTC. So I'll just come here and say place are placing an image, right? Pictures, NTC, and place it right there, then scale it up like that. Good. So anyone who needs to know how this device works can easily refer to the block diagram on page 1. Good. So I think time is up on that, and I hope you enjoyed this video. It's pretty long. If you watched this far, then it's good. If you've not, it's also fine. If you skip through the parts, it's easily understandable. But that's that. In the next design video, we are going to lay out this PCB and explain the design philosophy around the PCB, maybe review the different schematics. But yeah, so I want just to finish this design in like 3 videos or less. And yeah, thank you for watching, and maybe subscribe if you're interested in more videos like this, and leave a like. I've never actually, this is the first time that I'm saying this, to leave a like. And yeah, I'll see you on the next one. Have a nice one.